Good morning, good afternoon, and good evening. Welcome to Chapter 5. We are going to talk about cells and how they move things in and out. We're going to talk about a little more about chemistry. I know you're so excited about that. And then we'll talk about cellular movement. All right. So remember in Chapter 4 we talked about how the skin of the cell is two layers of phospholipids. In the picture, we can see the phospholipid bilayer, and we said that that makes a really good barrier to keep things, the good stuff inside and bad stuff outside. Remember that this is a phospholipid bilayer. It's got two layers of phospholipids. This gray ball here, this gray balloon, is the phosphate head. These two little tails coming off are the lipid tails. The phospholipid bilayer makes the skin of the cell selectively permeable, which means some things can come in and some things can't. The things that can make their way in are small molecules that are nonpolar. Remember we talked about what polar and nonpolar means. Polar means that it's got positive and negative areas, and nonpolar means it doesn't. One of the interesting things about phospholipids is that they are amphipathic, which means they are both polar and nonpolar. That phosphate head is polar, so it can mix with water. Those lipid tails are nonpolar, and they can't mix with water. This combination of polar and nonpolar is what makes the phospholipid bilayer so efficient and so effective at being selectively permeable, about keeping some things in and most things out. It's so good at its job at being selectively permeable, we have to give doorways because some things have to come into the cell. And we see in this picture a membrane protein. This membrane protein is a channel that allows some things to come into the cell. What kinds of things will use a channel like this to come into the cell? Molecules that are large and molecules that are polar. Those are things that will use these channels to come into the cell. So, cells have to bring things inside, and cells have to let some stuff, wastes, go outside. There are three different ways in which cells will bring stuff in or release things out of themselves. Three methods of what we call transport. Three methods that cells use to transport things into and out of the cell. The first method is called passive transport, and passive transport doesn't require the cell to spend any energy. The force that drives passive transport is called diffusion. Diffusion is the movement of particles from areas of high concentration to areas of low concentration. So imagine that someone's got a bottle of perfume, and they're standing in the corner of your living room. And they spray that bottle of perfume 2 or 3 times in that corner. I have a high concentration of perfume particles in that corner. Where is my area of low concentration? The rest of the room is the area of low perfume concentration. Are those perfume particles going to stay right there in the corner where it was sprayed? Or are they going to spread throughout the rest of the room? And we know this. It's going to spread throughout the rest of the room. It's going to diffuse throughout the rest of the room. Diffusion. The movement of particles from areas of high concentration to areas of low concentration. If you have two areas like that, lots of it here and not much of it there, you are said to have a concentration gradient. And what the particles want to do is to move down that gradient. They move from where there's a lot to where there's not much until the two areas are equal. That is the driving force behind diffusion, to make these two different areas equal. Because if I have two different areas, that means I've got stored energy between these two areas. And what I want is for the energy level to be at its lowest state possible. And the only way for that to happen is for them to be equal. And that's why the particles will move. The reason why we want it at its lowest energy state possible is because it is most stable, when it's at its lowest energy state. So, diffusion. Particles move from areas of high concentration to areas of low concentration. If I've got two areas like that, I have what's called a concentration gradient. And when the particles move, we say they move down the gradient. They move from high to low. From high to low means you're going down until they're equal. Here we see three images that show the movement of particles. I have my areas of high concentration right here, my area of low concentration. Please keep in mind and please remember that particles are constantly moving. The air particles in your house are constantly moving. The pollen that's floating in the air is constantly moving. Molecules are constantly in motion. Because they're constantly in motion, it means they're going to run into each other. They're going to hit each other, kind of like bumper cars. And so as these molecules are constantly moving, they will hit each other and will sometimes bounce away in different directions. And what will happen is these particles will start bouncing from where there's a lot to where there's less. And so it moves from where there's a lot to where there's less until what state happens? Until we reach what's called equilibrium, until they are equal. And that doesn't mean that the particles stop moving. It just means we're not going to have any net movement, which means here we've got 2 or 3 particles that move to the right and none to the left. Here we've got 3 or 4 particles that move to the right and 1 or 2 that move back to the left. And here we've got 1 or 2 that move to the left and 1 or 2 that move to the right. That means that yes, there's still movement, but there's no change in the number on either side. No average change. So that's equilibrium. This is diffusion. Moving from areas of high concentration to low concentration. The rate of diffusion is dependent upon 2 things. The rate of diffusion is dependent upon the size of the particle and the temperature of the particle. Temperature is easy enough. Hot particles move faster than cold ones. It makes sense. A really gross example is roadkill in December versus August. When you drive by roadkill in August, when it's nice and hot, how stinky is the roadkill? And the answer is, oh my God, it's awful. But when you drive by roadkill in December, how stinky is it? It's usually not, or not very at all. Well, why is that? What is the difference? The difference is how fast the particles move. When it's hot, they move a lot faster, and therefore they move a lot farther, which means they move a lot farther away from the dead animal. When it's cold, they don't move as fast, which means they don't go as far, which means they stay a lot closer to the dead animal. Very few of them move away or very far away from the dead animal, which is why roadkill isn't typically as stinky. When you drive by, I ain't saying walking, I'm saying drive. When you drive by in the winter versus in the summertime. Hot particles, and it's simply because the heat gives energy to the particle, making it go faster. Just like when you put your foot down on the accelerator, you give more energy to the engine, and it makes it go faster. Heat makes the particles move faster because they have more energy. The second one is the size of the particle, and this isn't maybe as easy to understand initially, and that is that small particles move faster than large ones. And the reason why has everything to do with their mass. How big is the engine in a semi-truck? Huge. It weighs like a ton by itself. How big is the engine in a motorcycle? Not very big. They probably weigh 60, 70 pounds. If the two of them are at a red light and it goes green and they're going to have a race, who's going to win? Well, in the short term, the motorcycle is going to win. Why? Because it has a lot less mass to move. The same amount of energy is going to allow the motorcycle to move a lot faster than the semi-truck because it has a lot less mass to move. Another way of looking at it, and it has 2 parts, and that is the same amount of energy will make a small particle move faster. The second part of it is a small particle moves faster because it can travel in a more direct line. Example. All right, imagine that we're at a big party, and there's dozens of people in this party. We're at a wedding reception. And I'm sitting in the one corner of the room, and I've got my 5-year-old son next to me. My son is not 5. My youngest is older than that. Just work with me here. I've got my 5-year-old son sitting next to me. His mom is all the way on the other side of the room, talking with some friends. And I look at my son and say, let's have a race. Let's see who can get to mom faster. On your marks, get set, go. And in this crowded room, people standing all over the place, who's going to reach my wife faster, me or my son? And the answer is the little boy's going to get there faster. And the question is why? Why is he going to get there faster? And the answer is he can take a more direct route. I have to go around people. I have to go around things. And he can occupy, or rather he can use smaller openings. So he's going to have a more direct route to get to his mom because he is smaller. Diffusion. The rate of diffusion is dependent upon the size and the temperature of the particles. Small particles move faster than big ones, and hot particles move faster than cold ones.